Okay, so as I'm sure you would be completely shocked to hear, I've already screwed this up once and taught this entire lesson or this entire example once and then realized I was not recording. So hopefully this is not a common occurrence, but one thing that I do get to do differently this time is my picture is now beautifully colored. So I hope you all appreciate that. These are the spikes in quality that I'm sure you're really hoping for whenever we do these kinds of example problems. So we're doing the first example problem for talking about conservative forces. This is the one that involves our Nerf dart here. Now, I have to apparently do this on a clock because during the last example, I realized the lights kicked out because I'm sitting in the middle of my classroom. And we don't want that. I'm going to try not to go super fast, but if the lights randomly shut off, well, you know what happens. The power didn't get cut on me or anything. All right, so we've got a Nerf dart, and that Nerf dart is compressed against a spring. And we're going to fire our dart. So that spring, when we release it, there's like a little clip or something that's kind of been pushing it back and holding it in place right here. We're going to release that clip. So that clip will be up, and that will allow the spring to then expand. It's going to stretch back out. And when it stretches back out, it's going to fire the dart. The dart's going to be fired forward. I assume you all kind of understand how these Nerf guns work, considering we did a whole lab on them. Now, our Nerf dart has a mass of 0.1 kilograms. It's 0.100, but I'm trying to save space here. And then it says it's loaded into the spring. The spring has a spring constant of 250 newtons per meter. And then we're going to compress it. It's been compressed 6 centimeters. Now, centimeters doesn't match meters, so we can just do a quick conversion to fix that. There are 100 centimeters in 1 meter, meaning we've got 0.06 meters worth of compression going on. Okay, now, in this case, we're going to treat this system as a whole. In the beginning, there's a certain amount of potential energy stored and a certain amount of kinetic energy, and at the end, there's a certain amount of potential and kinetic energy. Because this is a closed system, and because of the law of conservation of energy, E1 must equal E2. The energy at the beginning must equal the energy at the end. And if you remember, there's 2 types of energy, potential energy and kinetic energy. 2 plus KE2. Okay. Now, in this case, let's think about what's happening at each stage. To begin with, at our first stage here, is there any kinetic energy going on? I'll give you a moment to think about it. Shouldn't take too long, hopefully. While you might be running around with the Nerf gun and like it may be like getting thrown around and you're doing like dive rolls over furniture to make sure that you don't get shot by anybody else, in the gun itself, this dart should be held in place next to this spring. There should be no motion. So because our initial velocity for the stuff, everything involved, is 0, we don't have to worry about kinetic energy at the beginning. Now, what about here? Potential energy is coming from this spring being coiled, so there is potential energy going on here. But what happens when it expands? That potential energy, because it started from this point here, has moved. And energy of motion, cinetica, is kinetic energy. So that kinetic energy here is coming from movement, and it's being transferred to the dart. So the dart is also no longer still. That means that since both of them are not moving, so neither are still, we also get to cancel that out. There is no potential energy at the end. Now, you could say gravity is involved, but if you notice, all of our motion is horizontal, so we don't have to worry about gravity. So that only leaves us with potential energy. Our initial potential energy is coming from the spring. And if you remember, we have Hooke's law that we can do with springs. So we have 1/2 times K, which is the spring constant. And then we can do X, where X is the compression distance, and it's squared. So X is compression. I'm not sure if that's exactly the equation we used before, but it's the one I'm going to use this time. And then for our KE2, we're just going to use our same KE that we're pretty much always using, 1/2 mv squared. Mass we have back here, it's 0.1. And then velocity is what we're going to be looking for. So we can plug this in. Potential energy 1 is 1/2. Make sure it's on screen for you to see. Potential energy 1 is 1/2 kx squared plus 0, because there's no kinetic energy. Our potential energy 2 is 0, and plus our 1/2 mv squared. From here, you should be able to just work it out and solve it. This is a good point to stop. Even if you didn't understand how we got here, if you stop at this moment, you can make sure you know how to actually rearrange this and plug this in correctly. I'll give you a moment to do that. You can pause the video, but also I'm going to walk to the other side of the room so the lights don't turn off. So if you hear like tripping or anything like that, you know what happened. Send help. All right, that pause should have been awkwardly long enough, and I did get a drink of nice, refreshing, unbranded soda because I'm not currently sponsored, but if you have any beverages that are looking to sponsor a teacher doing content, have them reach out to me because I would love to make extra money. So we plug in. First, we want to get V by itself. We have halves on both sides, so we can just cancel those out. You can leave them in there, but or convert them to 0.5s, but they're not really doing anything, so I'm just going to cancel them out. Our V then, we would divide m to this side, and then we just have to do a square root to get rid of it. So we're going to have kx squared over m. That's all in a square root. And then we can just plug in all of our numbers. So square root, we're going to make this one look nicer than that because that looks really, really sketchy. We're going to do 250 newtons over meters. Our x, or distance of compression, is 0.06 meters squared. And then divide that by our mass of the dart. And our mass of the dart is 0.100 kilograms. Meters will cancel in this case, but then there's a squared here, so the meters will show back up. Kilograms down here will cancel with that, so we'll be left with a velocity. Our units that are left will be a distance over or time, or a velocity. So we can plug that in, and much to, I'm sure, Grace's huge annoyance, you will actually get a round number for this one. This whole inside of the square root right here will give you 9, exactly 9, I believe, if I remember correctly. And then square root of 9 will give you 3, but to proper sig figs, because I believe the question has 3 sig figs, you're going to want to do 3.00 meters per second. Now, this wouldn't be realistic because in reality there would be friction from the spring pressing against the sides of the barrel of the dart. It's not like you just have a spring floating in space, like in the void where it's actually going to be. But there'd also be some loss of heat. There's air resistance, all that kind of stuff. But we're ignoring that for this point. So this is a pretty straightforward problem showing how the potential energy in this spring over here gets converted to kinetic energy of the dart over here. So I hope that helped you figure out this example. Let me know after watching this, especially if there's anything that you think I should do differently. My setup will probably be different if I'm at my house. This is the best I could get working for school. Have a great rest of your day, everybody, and hope to see you / hear from you soon.